In October 2024, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Chemistry to Demis Hassabis and John Jumper. This was a highly unusual choice. Hassabis and Jumper are not traditional chemists working with physical compounds in a laboratory. They are computer scientists who lead the artificial intelligence lab Google DeepMind. They won the prize for building AlphaFold, a computational model that successfully predicted the complex, three-dimensional structures of proteins, resolving a mystery in biology that had lasted 50 years. But they didn't achieve this by asking a chatbot to read scientific textbooks. The system that solved it belongs to a different approach to intelligence, one that learns not by observing the world, but by interacting with it. Most of the AI systems making headlines today, like ChatGPT, operate on an observational logic. These models ingest massive volumes of human-created text. They analyze linguistic patterns from across the internet to mathematically predict the next word in a sequence. This approach hits a strict mathematical limit known as the data wall. The internet contains a finite amount of text, meaning the pool of recorded human knowledge that these models rely on will eventually run out. If a machine only learns by observing past human data, it is heavily constrained. It cannot synthesize a novel medical cure or solve a physics puzzle that humans haven't already figured out and written down. To push the boundaries of real science, artificial intelligence needs a mechanism to transition from passively reading about the world to actively generating its own original insights. DeepMind focused on reinforcement learning. Instead of reading text, an agent is dropped into a simulated environment, like a classic arcade game. It starts with zero knowledge, acting randomly through trial and error, driven entirely by one mathematical reward function, maximizing the score. As it plays, the system logs its successes and failures. It uses a technique called experience replay, storing gameplay data and reviewing it offline. This mimics how the human brain uses sleep to consolidate successful memories. This simple loop of action and reward scales up dramatically when applied to environments with millions of additional variables, like the ancient board game Go. These digital game boards serve as highly controlled physics engines. They give the AI a perfectly constrained sandbox, where it can safely fail millions of times to master the rules of cause and effect. This contrasts the data wall with the infinity machine. On the left, observational systems deplete finite human text. On the right, reinforcement learning generates data. Through self-play, it competes against itself, creating entirely original training data out of thin air. When deployed in real-world tournaments, the system executed moves and strategies that shocked human experts, because those tactics were never taught by a human programmer. By experiencing millions of simulated lifetimes, the machine bypassed human intuition entirely, synthesizing a level of strategic mastery that humans had never achieved. DeepMind eventually took this action-based logic out of digital game boards and applied it to biology's ultimate puzzle: how a linear chain of amino acids folds into a functional three-dimensional protein. The scale of this problem is staggering. A single protein can fold into more potential configurations than there are atoms in the observable universe. Brute force guessing is mathematically impossible, but researchers hit an obstacle. Biology lacks the clear rules of a two-player video game. Nature doesn't provide a digital scoreboard or a predefined winning state to guide the algorithm. To solve it, the DeepMind team had to merge these two distinct methods together. They utilized the transformer architecture, the engine behind large language models, to read the sequential language of amino acids. Then they combined that text reading capability with the spatial reasoning and problem-solving structures honed by their video game agents. By treating the natural world as a dynamic physics simulation rather than a static text prediction problem, the AI was finally able to map the building blocks of life. AlphaFold successfully predicted the structures of virtually all 200 million proteins known to science. This complete biological map bypasses decades of grueling manual laboratory work, replacing complex physical experiments with near-instant computational predictions. This represents a turn away from purely observational models, like chatbots, and towards agents that learn by doing. The next generation of models will be tasked with interacting with, simulating, and decoding incredibly complex natural systems, accelerating research into genetic diseases, discovering entirely new medicines, and designing advanced materials. The 2024 Nobel Prize serves as proof that the future of artificial intelligence lies in action, not just observation.